Okay, so in this lecture, we are going to cover naming fused ring systems, okay? And so you can see this ring system down here, all right? You've got a 6-membered ring and a 4-membered ring here, and they're connected here and here, right? So how do you go about naming these when you have two rings put together? And there's actually a general formula, and it's this down here, which sort of makes it pretty simple to name, right? So when you want to name a compound like this, there's actually a fairly straightforward procedure. And one is to count the number of rings. So you have some sort of N, and that can be a bicyclo, a tricyclo, etc. Okay? And then you label them with the number of carbons or the number of atoms in the large ring, the number of atoms in the medium ring, and then the number of carbons in the smallest ring. Okay, so this is pretty much universally true. And then the root alkane. All right, so if you look at this structure that I've drawn up here, you can see that there's this tertiary or secondary carbon right here. So it's got 1, 2, 3. So it's got a proton or a hydrogen here and here. So they've got some uh, uh, secondary carbons on those positions. And these are what are called bridgeheads because these two carbons connect this ring on the left with this ring on the right. And so when you start counting in these fused ring systems, you count from the bridgehead. And you count from the bridgehead, so you can pick either one, and you start moving in the direction of the larger ring, right? So if we go this way, we get 2, 3, 4, 5, 6, 7, 8. All right. And so you can see I moved this way first because this over here has 4 carbons over here. And then I move over to this side of the ring and it's got 2 carbons on that side. Okay. So if we look down here at our nomenclature, what do we have? We have a bicyclo system because there are 2 rings in it. So that way that we write the this out as a bicyclo system. All right, and then we start our bracket. And what's the largest ring have? How many carbons? And it's got 1, 2, 3, 4. That's easy. 4 dot. What's the medium one? All right. Well, so this implies that there are 3 rings, right? 1, 2, 3. And in a bicyclic system, you would take the medium ring to be the smallest ring. So there's only 2 carbons there. And then what's the actual smallest ring? And the smallest ring is actually this bond that connects 1 and 6, right? If you look between 1 and 6, you will see 0 carbons. There's no carbon in between here and here. So that's 0. So if you have a bicyclic system that is simply fused with nothing in between, you have a something with a 0 in your smallest configuration. And then your alkane, because you've already called it a cyclo, you call your alkane essentially just the number of carbons. So this is an 8-carbon chain, so this must be octane. Now, we can get a little bit more complicated, right? So if we draw something that is a 2 carbons, right? So 2-carbon bridgehead, like this, okay? So we see here now our connecting carbons here and here, okay? And then there is this carbon right in the middle. So if we look and we can go, when we start numbering, there's 2 carbons on this side of the bridgehead and 2 carbons on this side of the bridgehead. So in that sense, it actually doesn't matter which direction we go, so we can go in either. So we'll just 2, 3, 4, 5, 6, and then we hit the one in the middle, the smallest bit, right? So what we want to look at now, here's the question. How many rings? So is it a tricyclo? Is it a bicyclo? We can actually, this is, of course, all 3-dimensionality. So we can actually draw this structure in 3 dimensions, and maybe it might help just a little bit better to see how many rings we've got here. So this is that structure drawn three-dimensionally. And you can see it's actually only got 2 rings, okay? And is there a way to assuredly know that you've only got 2 rings? Yes, as a matter of fact, there is. How many cuts do you need to make to this structure to make it just a straight chain, 7-carbon chain, all right? So if we redraw this, how many bonds do I have to cut to make this a 7-member chain? And I can just show you. So if I just take that one, I took too many of them. If I just take that one out, all right, then I still have this part is still a chain right here. That's still a cyclic compound right here. But if I take this part out, now I have a chain. When that chain, it's substituted, but it is a straight chain. It looks like this. 1, 2, 3, 4, 1, 2, 3, 4, and then I've got this little weird substitution pattern here. So that's a straight chain, right? There's no cycles in it at all. But the point isn't that the carbon counts or any of that. In order to get rid of all the cyclic systems, I made 2 cuts, which means it's a bicyclic system, right? So if I had to make 3 cuts, it would be tricyclic. So we can rest assured that in this particular case, we have a bicyclo system, right? And then we can now create our brackets. And in this system, our large cis chain is 2 carbons, right? 2, that's a 2. Our medium one actually is the same size as our large one. That's a 2 and a dot. Now our smallest one is in between these 2 bridgeheads here. There's a 1 carbon spot right there. Okay, so that's a bicyclo. Let's move this down a bit. And then we write the name of the alkyl, the parent alkane. And how many carbons did we count? We counted 7. So if we count 7, then the name heptane, so bicyclo 221 heptane. Okay, now what do you do if your system has substituents on it? How do you go about labeling that? Put a bridgehead there, say a methyl group there, and a methyl group there. All right, so this looks suspiciously like this, right? Sort of this bicyclo 221 heptane, which actually has a common name since it's encountered so often, believe it or not, and that's called Norbornane. Norbornane is actually seen quite frequently in organic chemistry. And this has that Norbornane look to it. And if you do the same sort of 3-dimensional flippity-flop, this is going to challenge my drawing skills, which is great. I love that. And then it's going to have some sort of dippy carbon here. And then we've got a carbon coming up here, right? Actually, I can draw that better. I know I can. We can draw the carbon coming up here and down here. And we got a methyl group coming out here and a methyl group coming out there. All right. So whichever one is easier for you. Most people in their sophomore year don't really have the ability to see how that, the one on the left, corresponds to the one on the right. But they in fact do. They're the same structure. And so depending on how you want to start, let's just say we can start at our bridgeheads here. All right. And now this is interesting. We know that one of these is going to be 1. And then we're going to have to go around the big loop first. So we can go 2, 3, 4, 5. And then we know we can go around the little loop, 6, or medium-sized loop, 7. And then we got to get the one on top, 8. All right. So, and to re-illustrate that over here, what did I do? I started down here in 1, 2, 3, 4, 5, 6, 7, 8. Okay. I there's not really any particular reason why I started counting there. I know that my substituents ultimately have to be labeled so that the numbers are the lowest, and that may or may not have been correct. So let me just see if I can recount this to see if I can get those methyl groups to be on the smallest numbers. All right, so if I count the other way, like I go up here, I still have to go around my big loop. 1, 2, 3, 4, 5, and then this one is 6, 7, and 8. Right, so numbering this way puts a methyl group. Now I can't get away from a methyl group at the 8, but if I count this way, I get my methyl group on the 6. Whereas if I count up here, I get my methyl group on the 7. So I have to count this way, so down here, so that my methyl group is substituted on the 6, all right? And so this, now that we've got our counting out of the way, just like when we labeled cyclic systems first, we put the substituents out in front. So when we did that, that was always some sort of dimethyl. So we would call that, 6, 8 dimethyl. And that's how we would label those substituents. And then while we have a bicyclo system, because this is, you can do your cuts if you'd like, but this is definitely a bicyclo system. All right, and we open our parentheses, and the number of carbons in our big chain, we can count those. 1, 2, 3. All right, so that's easy. 3. Number of carbons in our medium chain, that's 2. And then the number of carbons in our small chain, that's 1. All right, easy peasy. And then the final one is just your central carbon count, right? So in total, this system has 10 carbons, because if you count these carbons out here, you can count a 9 and a 10. But those are not part of the bicyclo. Remember, you're looking at the root. And the root is the cyclic system. And that cyclic system actually only has 8 carbons in it. So octane. You've accounted for 9 and 10 out here, so that's where you account for 9 and 10. So your overall structural name is 6,8-dimethyl bicyclo 3,2,1 octane. Okay, now let's go a little crazy. Let's look at this cyclic system. All right, this is called Cubane. It's pretty nuts, right? So it's carbons all connected at 90-degree angles. And remember, carbons like to have 109-degree angles because they're all sp3 hybridized. So carbons normally like to be at 109-degree angles, and these are all forced at 90-degree angles. So this is hella energetic. This really wants to go nuts and explode. And some people have postulated that this would be a great high energy explosive if you turn these hydrogens into nitrogens. Like, wow, crazy. So anyway, you can make this molecule. It's and it does have a fused cyclic system, and it's a little bit more challenging to actually look at how you're going to name this. So it's some kind of cyclo, but the question is, of course, is it bicyclo, tricyclo, what? Well, we can pretty simply just do some cuts, right? How many cuts does it take to make this an alkane, and straight chain alkane? And so if we keep track of our cuts, this should help us. And to do that, let's just start cutting. Let's see here. 1, 2, 3. I took out 2 there at the same time. Hold on. 1, 2, 3, 4. Let's see here. There's a little thing back there. So let's see here. I'm gonna make my little eraser partial. We're gonna do this a little bit. So we're gonna go with cut first here, 1. Yes, good, good. We cut this one, 2. That looks fine. Let's cut the one in the back, 3. And then, of course, there is this little lagging thing right here. I'll cut that thing. 3. Let's get rid of this one here. 4. We still have a cyclic system here. That looks like 5. And let's see. It looks like there's no more fused rings here. 5. Let's see what connects here, connects here, connects here. Yep, that's it. All right, so it took 5 cuts to get to the center here, and so this must be a pentacyclosystem. That is pretty crazy. Not sure how one would have come to that conclusion without doing a couple cuts, but that's fine. Let's put this back together because now we've got to figure out some bridgeheads. So we'll put our carbon cube back together, our bizarre little Borg cube, and we know that it's a pentacyclosystem, so we can go ahead and keep that down here. And what we need to be able to do is we need to get it down to at least a bicyclic system in order to start giving it some numbers. We can look at this structure and see that if we get rid of, say, this carbon here, this here, and we can get rid of this here. Let's get it down to something digestible. And the most digestible for me is a bicyclic system. And there. So now we've got it down to a bicyclic system here. And I can highlight this bicyclic system a little bit better, is that you've got this one cyclic system there, and then you've got a second system that is shared with this bridge here, and it is this system there. All right, so that we can name. All right, and if we do name it, it kind of goes, we got to start at a bridgehead, 1, and then we count the big one first, and then the small one. Okay, so pentacyclo, and we draw our bracket, and we have a 1, 2, 3, 4 membered ring, a 1, 2 membered ring, and a 0 carbon bridgehead. So from our bridgehead now, we've got make some reconnections because these are going to be the rest of our pentacyclo system. So let's move this a bit over. And there are a couple bridgeheads that I had to erase to uncover this small bicyclic system. And there's a bridgehead between 2 and 5. And so, but there's no carbon in there. So we can still call that 0. And to be clear, that 0 corresponds to the 2 and the 5 position, right? And then there is a connection between 3 and 8 that I also deleted, right? So no bridgehead there either. So that's gone. And then I deleted this one over here between the 4 and the 7. And from there, you can see how it's a pentacyclic system, right? One cyclic is a fused 4-2 with a 0-headed bridge carbon, and then 2 more 0-headed bridge carbons. And we can close that up, and then, because that's all our bridging, and then give it its parent structure name, which is 8 carbons, so that must be octane.